In section 6.2, we're going to continue our study of applications of calculus and the derivative by looking at something that's used in physics, the concept of distance, velocity, and acceleration. This is really just a continuation of 6.1 where we looked at rates of change, except in this case, the function isn't just an arbitrary function called f of x, but suppose we had a function that described the position of an object as a function of its time. So what I've done here is drawn just an arbitrary function for you. This function just represents the location of an object or its position at any moment in time. Now we saw in 6.1 that the average rate of change was the slope of the secant line. Well, let's investigate what happens in the case of this graph. So let's say we picked an arbitrary moment in time right here and we called it t1. So just an arbitrary moment in time. At that particular moment in time, the object would be located at some position. That position would be the position S at t1. Now suppose that the object had moved and we were investigating it at some time later. So let's say we picked a second time and we called it t2. Now obviously the object will have changed its position, and so its position will be indicated by S at t2. Now if we join those 2 points with a line, we have what's called a secant. Now we know from 6.1 that that secant slope is the average rate of change. Well, let's see what happens in this case. Our rate of change, our average rate of change, is just the slope of the secant, which in this case is delta S, the change in position, divided by the change in time, delta t. Or if we use our function, it would be S at t2 minus S at t1 all over t2 minus t1. I want to stress that what we're doing here is exactly the same as 6.1. The only difference was in 6.1 it was just a function called f of x. In this case it's a position function called s of t. So the question becomes, what have we actually found? Well, if you just think about it logically, we have an object that has moved its position, so it's traveled some distance over some given interval of time. And you probably know this from science or physics that if you investigate how far something has traveled divided by how long it took to get there, we call that velocity. So what we've actually found here, this average rate of change, is really called the average velocity. So we would just say that the velocity, average velocity, is just equal to this formula right here. So what we're going to investigate in 6.2 is the same math that was investigated in 6.1, but now it's going to pertain to the concepts of distance and velocity and acceleration. But of course, what if we didn't want to find the average velocity? This is just going to tell us on average how fast this object was traveling between the two times t1 and t2. What if we wanted to know how fast it was traveling precisely at an indicated time? So now what's happening is, so if we drew a picture here, it's the same setup. We have the position of an object at some moment in time, and the object is traveling like this. What if the question now was saying, right here at this time called t1, what if we wanted to know how fast the object was traveling? What is its velocity at exactly that point? Well, that would be the rate of change of the graph or the function at t1, which of course we call a derivative. So it turns out that if you want to find what's called instantaneous velocity, so we would just say velocity instantaneous is just going to be the derivative of the function s of t. So s prime of t will give us our derivative. So in other words, the velocity function v as a function of time is just equal to s prime of t. So one of the applications of calculus is when you're studying the motion of an object, without calculus, the best we could do was find on average how fast it was traveling between two given points. But if you happen to know the position of an object at any moment in time, if you take the derivative of that position function, you will find the slope of the tangent line. But the slope of a tangent line, of course, is just the instantaneous rate of change. And in the case of a distance time graph, the rate of change is called the velocity. So now this gives us the ability for physicists to have the ability to analyze at any precise moment the exact velocity of a given object. So again, just to summarize, in 6.1 we talked about rates of change. Well, it turns out that velocity is a rate of change. Velocity is the rate of change of distance with time. So we could find average velocity by finding the slope of a secant line, or we can find the instantaneous velocity by finding the slope of a tangent line, which of course is called a derivative. Okay, so let's look at an example of a velocity question. So what we have here is a ball rolling along the x-axis. So what I've drawn over here for you is a representation of what's going on. What we have here is an object that's traveling in a straight line. So this line right here, which is the x-axis, has a starting point called the origin. We are investigating an object that's moving and that in such a way that its position is given as a function of time by the formula t cubed plus 3t squared, and we're only investigating the question starting at 0 and all positive values of time. So for example, at time 0, the object would be at the origin. If you plug 0 into here, we find out that the answer would be 0. So the object is starting right here at time 0, and then the moment it takes off, the object is going to start moving. And we don't know right now whether it's moving left, right, or whether it stops, turns around. We just know that the object is traveling along the x-axis, and it's traveling so that its position is given by this function. So the first question says, find the velocity average between 1 and 5 seconds. Well, average velocity is just a secant slope. So average velocity would just be the change in distance, s, the change in position, divided by the change in time, t. Between 1 and 5 seconds, our position is going to be s at 5. If you plug 5 into this function, we'll get 125 plus 75, which means that the object was located 200 centimeters away from the origin after 5 seconds. So the object is over here somewhere at 200 centimeters at 5 seconds. After 1 second, the object would be simply at 1 plus 3, which is 4. So after 1 second, the object was located right here at 4 centimeters. Now, using the secant slope, we can find the average velocity between those two moments in time. So average velocity will just be the difference in the distance that's been traveled, so 200 minus 4, or 196 centimeters, divided by the interval of time, which is 4 seconds. So we get an answer of 49 meters per second. But again, you see how that's limiting. It doesn't tell us exactly what the object was doing at any moment in time. It just tells us that as it traveled from 4 centimeters to 200 centimeters, it was traveling on average for those 4 seconds, it was traveling 49 meters a second. We're more interested in finding the velocity at precisely 1 moment. So what if we want to know at the moment that the object reached this 200 centimeters, what if we wanted to know precisely how fast it was going? Well, that's called instantaneous velocity, or we just say velocity. So the second question says, find the velocity at 5 seconds. Well, instantaneous velocity is a tangent slope. So to find the velocity v of t, we simply need to differentiate our position function. So we're just going to find s prime of t. So taking the derivative, we get 3t squared plus 6t. This is called the velocity function, and this is telling us how fast the object is going at any precise moment in time. Now the question wants us to find the velocity at 5 seconds, so we just go v at 5 equals 3 times 5 squared plus 6 times 5, or 105 centimeters per second. So what this is telling us is that 5 seconds after the object left the origin, we know that it's located right here at 200 centimeters. We know that at that precise moment, it is traveling with a positive velocity of 105 centimeters per second. So we know it's traveling to the right and at precisely 105 centimeters per second. A lot more descriptive than simply finding an average velocity. So average being a secant slope, or average rate of change, and instantaneous velocity being the tangent slope, or the derivative or the instantaneous rate of change. The last question is a little more thought-provoking. The question says, where is the ball when its velocity is 72 centimeters? So this object has left the origin and is traveling along the x-axis, and we want to know where exactly is it on the x-axis when it has a velocity of 72 centimeters per second. So we have a velocity function. So our velocity function says that the velocity of the object at any moment in time is 3t squared plus 6t. So this will tell us the velocity at any moment in time. But we can also use the function in reverse. We know the velocity is 72 centimeters per second. So if we replace velocity with 72, we'll end up with an equation that will allow us to solve for time. Now the time will be whatever values of t make this equation true. So what we have here is a quadratic equation. So the thing to do with a quadratic equation is make it equal to 0. So 3t squared plus 6t plus 72. And then we want to solve by factoring. We can take out a common factor of 3, t squared plus 2t, and sorry, this would be a minus 72 right here. So we end up with minus 24 equals 0, or 3 times t minus 4 times t plus 6. So we're looking for would make this equation true. So we would get times of 4 seconds and negative 6 seconds. Now since we're only investigating the object for positive values of time, the negative 6 would be an extraneous root and we wouldn't be interested in it. So this tells us that 4 seconds after the object left, it was traveling with a velocity of 72 centimeters per second. But the question is asking is for its position. Where is the ball at this particular moment? So the position function is s of t. But now we know at what time this is happening. So what we're going to do is we're just going to go s at 4. In other words, what is the position of the object at 4 seconds? So if we plug 4 into that function, we will get 64 plus 3 times 16, or 112 centimeters. A positive 112, so over here somewhere. So you can see by using calculus, by simply taking the derivative of a function, which gives you its velocity, we could now analyze the entire life of this particle. When was it stopped? When was it moving to the right? When was it moving to the left? All by simply analyzing the velocity function and the position function. So we have seen that if you have a position function and you take its derivative, you get the rate of change of position, which of course is velocity. So the next question we should ask ourselves then is, what if you had a velocity graph? What if you had velocity as a function of time? Obviously, we could perform the same math on that function. We could find, for example, the slope of the tangent to a velocity graph. Well, we know that the slope of the tangent is a rate of change. So what is the rate of change of velocity? Well, you probably know that that's acceleration. Whenever velocity changes with time, we have what's called acceleration. So if we take v prime of t, in other words, the derivative of the velocity function, we will get what's called the acceleration function. Or using the Leibniz notation, if we wrote dv dt, the derivative of velocity with respect to time would be acceleration. So using calculus and derivatives, we now see that you can take a position function and you can now analyze the particle, not only its position, but its velocity and its acceleration. So just a quick summary here, just to summarize what we've done in this section. If we're given the position function of an object, if we're given the position function s of t of some object, then using the concept of a derivative, we can analyze the velocity. So the velocity function v of t would just be s prime, or the derivative or rate of change of the position function. And the acceleration function a of t would just be the derivative of the velocity function v of t, or using a symbol we learned earlier, it'd be the same as if we took s double prime of position, the second derivative of the position function. So you can see now that just with the simple concept of a derivative, in physics, we can now take an object, and as long as we know its position, we can analyze exactly where the position is at any moment in time, how fast it's traveling, whether it's accelerating or decelerating. Quite a powerful tool. So if we go back to the example that we were looking at a few moments ago, you may recall we had an example where the position of an object s of t was given by t cubed plus 3t squared, where t was greater than or equal to 0. And we had determined that the velocity function v of t would just be the derivative 3t squared plus 6t. Well, now we could ask ourselves a question. So I think the next question was D. We could say, what is the acceleration of the ball when t is 1? Right? So what if you want to know what was the acceleration of the ball at time equals 1? Well, we know that the acceleration function, a of t, is just the derivative of the velocity function. So it's just v prime of t, which according to our power rules would just be 6t plus 6. So now we have a a function that describes the acceleration. And so the acceleration at 1 would be 6 plus 6, or 12. And our units would be meters per second. That's velocity per second. We're doing velocity over time. If you look up here, it's a velocity divided by time. So meters per second, which is meters per second squared. And those are our units for acceleration. So we'll continue with this example now. We'll just keep going here. We'll do part E. Part E. What is the velocity of the ball when acceleration is equal to 54 centimeters per second squared? I've got centimeters here and meters here. I forget now in the question what our units were for that, but anyway, it's whatever the distance units were, meters or centimeters. So what is the velocity of the ball when the acceleration is 54 centimeters per second squared? Well, now we have to start thinking about what we're trying to find here. We have three functions. We have the position function of the object, we have its velocity function, and now we have its acceleration function. And so you just have to now do some critical thinking and say to yourself, what is it exactly that we know? Well, we know that the acceleration is 54 centimeters, so 54 would be our A value. So that's going to be plugged in here for A. So we're going to say 54 is equal to 6t plus 6. Now you can see that that's going to enable us to find time. If we subtract the 6 and divide by divide by 6, we'll get a value of 8 seconds. So what we now know is that the object was accelerating at a rate of 54 centimeters per second squared after 8 seconds. And the question wants us to find the velocity of the ball at that moment. So we have to go back to our velocity function, v of t, and we know that the time is 8 seconds. So we're just going to go v at 8, which turns out to be 240, I think it was meters per second. Okay, now that we've seen that we can take a position function and differentiate it to get the velocity function, and then differentiate that to get the acceleration function, it's now possible to analyze the motion of an object pretty much as we want. So it's really quite powerful. We can now take a position function, in this case it's a B flying along the x-axis, and we're told its position as a function of time for positive values of time. Now, based on that function, in theory, we could now analyze the entire lifespan of the travels of this bee. We could find out where it is at any moment in time, how fast it's traveling, whether it's moving in a positive direction, a negative direction, not moving, accelerating, decelerating. All of this can be now determined by simply differentiating the functions. So what we'll do here is go through a series of questions. The first one says, where is the bee located at 3 seconds? So the purpose of the first question is, just so I want you to get used to understanding what function you want to use. Where the bee is its position. So all this question is asking us to do is to find S at 3. So what we'd do for the first question is we would just say the position of the bee at the time 3 seconds is equal to, and then we would just plug the value of 3 into our function. Now I've done that already so we can save ourselves some time, but I'm plugging the number 3 in here for time, so I'm going to have 2 times 3 cubed minus 21 times 3 squared plus 60 times 3, and the answer turns out to be 45 centimeters. So you see, by answering that question, I can now tell you something about the bee some moment after it left in its travels. Right now, if this was the actual number line that the bee was on, and this was the origin 0, at 3 seconds, I now know that the bee is located over here at 45 centimeters. The next question says, what is the bee's velocity at 3 seconds? So now what this question is asking is, now that I know where the bee is located, I'd like to know how fast it's traveling. So what I need to do is find the velocity function. So the velocity function, v of t, of course, is the derivative of the position function s prime. So that would give us 6t squared minus 42t plus 60. So you see that I've created a brand new function now, and this function will describe the velocity of the bee at any moment in time. So to find the bee's velocity at 3 seconds, I'm just going to plug the number 3 into the velocity function v of t. So that would be v at 3. And again, I've done that already. If you plug 3 into here, I'm plugging it in for time. So 6 times 3 squared minus 42 times 3 plus 60. The answer turns out to be negative 12 centimeters per second. So now, not only do I know where the bee is located at 3 seconds, right here at 45 centimeters, but I know it's traveling with a negative velocity, which means to the left, at negative 12 centimeters per second. So now I know that the bee is traveling back toward the origin at a velocity of 12 centimeters per second. The next question says when was the bee not moving? So again, we just have to ask ourselves, well, what physical trait does that mean? If the bee is not moving, then it has 0 velocity. So I need to take the velocity function right here, v of t, and I'm looking for the time. When was the bee not moving? So its velocity is going to be 0. So what I'm going to do here is I'm just going to plug the number 0 in for the velocity. So I'm going to say v of t equals 0, which gives me 6t squared minus 42t plus 60 equals 0. Now to solve this, you have to recognize what kind of equation you have. This is called a quadratic equation, so we need to factor it. First of all, there's a common factor of 6, so we can take the 6 out, and we'll be left with t squared minus 7t plus 10 equals 0. And then the trinomial that we are left with can be factored into t minus 5 and t minus 2. So 6 times t minus 5 times t minus 2 equals 0. And we're looking for what values of time would give us 0 for a velocity. We have 3 factors being multiplied together here, 6 times t minus 5 times t minus 2. In order for the result to be 0, one of these factors must be a 0. Well, it can't be the 6. The 6 is a constant, so it must be when t minus 5 is 0 or when t minus 2 is 0. So it turns out that the bee is not moving at 5 seconds and at 2 seconds. So twice during the life of its travels, it was actually stopped. And the last question says, when was the b moving to the right? Well, if the b is moving to the right, on a number line, to the right is a positive value. So what we're looking for here is, when is v of t greater than 0? So now what we have to do is equation right here, our velocity function, and solve it for not equal to 0, but we have to solve it for 6 times t minus 5 times t minus 2 is greater than 0. Now, I picked this question because I thought this would be a good time to review with you how to solve a quadratic inequality. That's what we call this, a quadratic inequality. And to do that, we use what's called a sign analysis. So what we would do is draw ourselves a number line. And on that number line, we would mark off our critical numbers. We have 0, 2, and 5. And then what we do is we look at all of the different factors. We can ignore the number 6. The number 6 is always positive, so we don't need to include that. The t minus 5 and the t minus 2, however, will need to be analyzed. So if we look at the t minus 5 as a factor, we know that we're going to have our function here is only defined for greater than or equal to 0. So we're going to have a square bracket here at 0. And then if you plug in numbers between below 5, so if you plug in 5 into here, you're actually going to get 0 for an answer. If you plug in anything between 0 and 5 into this factor, we're going to get negative values. So these are all going to be negative values up to here. And these are all going to be positive values if we plug them in beyond 5. If we analyze t minus 2, t minus 2 will be 0 at 2 with a square bracket here. And this time it's going to be negative for numbers less than 2 and positive for numbers greater than 2. Ultimately, what we want here is we want v of t greater than 0, which is t minus 5 times t minus 2. So if we multiply these factors together, in this region right here from 0 to 2, we have negative times a negative. So of course that's going to give us a positive value. So our product is going to be positive in here. It's going to be square bracket, and then it's going to be positive. This will be 0 because negative times 0 is 0. This will be a negative times a positive, which will be a negative. This will be 0, and this will be positive. And this is going to keep going forever, so it will be a round bracket. Now, based on this, our chart here, our sign analysis, we can now say that the object is moving to the right when it has a positive velocity. Well, it has a positive velocity from 0 to 2 and from 5 to infinity. So we would say for the answer that the object is moving to the right at square bracket 0 up to 2 seconds, round bracket. You notice it's a square bracket because right at 0, the object does have a velocity of 60. The b did not take off at 0. It was actually, we started keeping track of the time at 0, but at time 0, the velocity would be 60. And then union, round bracket, 5 to infinity. We're going to finish off this section right here with another example. So far we've been focusing on questions where we have an object moving along a straight line like the x-axis. But in this case it's more of a realistic question. What if we have a rock that's being thrown upwards from the top of a house and its height above the ground is a function of time? So what we have here is height as a function of time of a ball being thrown off a building. So the first question says, find the initial height. So again, the reason for these questions is I want you to start thinking critically about these formulas. So we know that if we differentiate this function, we will get velocity, and if we differentiate again, we'll get acceleration. But you have to ask yourselves, which function do we want to use in this case? Find the initial height. Well, so obviously we want the height function, h, and initial would be at the moment the ball was thrown, which would be time 0. So what the first question is saying is, what is the height h at time 0? So we're just plugging 0 into our height function. So obviously the t terms will disappear, and we'll just get the answer 5. So the rock was 5 meters off the ground at that particular moment. The next question says, find the velocity at 2 seconds. Well, now the velocity, of course, is not our height function. The velocity is the derivative of the height function. So what we have to do is find our velocity function v of t, which of course is just the derivative of height, or position, h prime of t. So using our power rules, we get negative 10t plus 40. So that would be our height function, and the question wants us to, or sorry, that would be our velocity function, and the question wants us to find the velocity at 2 seconds. So the velocity at 2 would just be v at 2, which would give us 20, and the units would be meters per second. Question C, find the acceleration at 2 seconds. Well, we know that acceleration is the rate of change of velocity, so we need to differentiate to find our acceleration function a of t. We need to take the derivative of v of t, so v prime, and what happens is we just get negative 10. And I thought this was kind of interesting to discuss. You'll notice that the acceleration does not have a value of t in the function, which means it's a constant. The acceleration at any moment in time is always going to be minus 10, and the units would be meters per second squared. And if you've taken a little bit of physics, you may recognize that that number is close to the actual value of acceleration due to gravity, which is negative 9.8 meters per second squared. In this case, the value of this value here was just rounded off to 5 instead of 4.9, but this actually indicates what really happens when you throw a rock off a building. It's going to always accelerate toward the ground, and it accelerates at a constant acceleration independent of the time after it's left from being thrown. So you'll notice that there's no place to plug the time in because it's always constant. When does the rock reach its maximum height? This is an interesting question to think about. So what are we actually trying to find here? So if you imagine that an object is thrown off, this is the building here. If the object is thrown off the building, it's going to go up like this and then come back down and hit the ground. So when it reaches its maximum height, you have to ask yourself, what do we know about the rock at that point? Well, its maximum height is right here, which is the peak of the graph. Now, we saw in our graphing section that at the peak of a graph, the tangent is horizontal. Now that we've studied velocity and acceleration, we can see what's actually happening. When you throw a rock into the air, it actually comes to a stop at the moment it reaches its maximum height. In other words, the derivative or the slope of the tangent is 0. So when does the rock reach its maximum height? Well, it's going to reach its maximum height when its velocity is 0. So our velocity function was negative 10t plus 40. So solving that for time, we can find out that the object was actually at its maximum height 4 seconds after it was thrown. It's interesting the number of applications we can now solve with this idea of derivatives and acceleration and velocity. What is the maximum height? Well, to find the maximum height, we need to go back to our height function. But to find height, you need to know the time. So, of course, that's why we did question D. We know it took the rock 4 seconds to reach its maximum height. So what is the maximum height? It would be the height at 4 seconds, be h at 4. And if you plug 4 into your height function, you will get the answer 85 meters. And our last question, with what velocity does the rock hit the ground? A lot of people think that when the rock hits the ground, it has no velocity. Well, it has no velocity because the ground stops it, but it actually does hit the ground with a velocity. If you were standing there and it hit you in the head, you would attest to the fact that it does have a velocity when it strikes the ground. The velocity when it strikes the ground is going to be the slope of the tangent at that point. So we need to find the velocity when the rock hits the ground. Well, our velocity function dictates that we have to have the time. So we need to know how long it took the rock to hit the ground. So again, it's a nice thought-provoking question. What do we need to know to find when the rock hit the ground? Well, when it hits the ground, it's going to have no height. Its height's going to be 0. So if the height is 0, we can solve the equation 0 equals negative 5t squared plus 40t plus 5. This will tell us at what moments in time the object had a height of 0, in other words, was on the ground. Now we can divide both sides of this by -5 because it's equal to 0. So we're going to have t squared minus 8t minus 1. You'll notice that this quadratic equation is not factorable. So what you're going to have to do is resort to something that you learned a while back called the quadratic formula. The quadratic formula says that the roots to a quadratic equation, in this case t, are equal to plus or minus b, which would be 8. Sorry, not plus or minus b, just minus b, plus or minus the square root of b squared minus 4 times a times c, which would be 8 plus or minus the square root of 68 all over 2. I forgot to divide by 2, I'm sorry, up here. All this would be divided by 2a. I'm sorry, the quadratic formula, again, is, maybe what I'll do is write that down for you. Since I messed it up, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, of course, it's not x, we're solving for time. Our values of a, b, and c are our coefficients. A would be -5, a would be 1, sorry, b would be -8, and c would be -1. Now we could find the exact answer, but in a question like this, it makes more sense to find an approximate answer. So if you actually type this into your calculator, you'll get two approximate answers. You'll get about 8.1 seconds and about -0.12 seconds. If you're wondering why there's two answers, the quadratic equation doesn't know that we're solving a problem of a rock being thrown off a building, so it actually thinks that this parabola is going backwards and going to hit the ground, which is why it's giving you two intercepts. We, of course, can ignore the -0.12, and it takes 8.1 seconds for the rock to hit the ground. So the question was, with what velocity does the rock hit the ground? So we're going to plug the 8.1 seconds into our velocity function. So velocity at 8.1 equals, so we're going to get -10 times 8.1 plus 40, or -39 meters per second. So that wraps up our study of velocity and acceleration, a very important part of calculus. If you go into the sciences, especially physics or engineering, we do a lot of work with calculus and derivatives because it helps us analyze motions, the motions of particles.